Hello. In this video, we will look at this integral. It may not look too friendly, but that's because it's educational. It's supposed to make a point. Or two, or, well, we will see. Okay, let's start. I have an integral here and I'm thinking, which method should I apply? I have three of them, so let's see. Integration using partial fractions. Not really. This is not a ratio of polynomials, so that's out. Nice. Substitution. Is there something I can simplify? Well, I guess so. I could get rid of this square root and it would become nice. And the third possibility is integration by parts. Do I see integration by parts there? Well, there is a product here. If I try to apply integration by parts, I would have to take this part and differentiate, and this one and integrate. I don't feel like it. How about the other way around? I differentiate here, I integrate. I'm not too happy about this idea. So substitution seems like the best bet. So I would like to take this square root and call it y, but just to make my life easier, I will instead try the indirect substitution. So I take x and I replace it with t squared. Now, this will make the formula most likely nicer, and I can find the formula for replacing dx also easily. So that's one of the advantages of the indirect substitution. You get the formula for dx right away. And we can do the replacements. So I see square root of t squared divided by t squared times, and here we have square root of t squared plus 1, that all squared, arctangent, square root of t squared, and here we have 2t dt. And now we need to figure out what it actually is. Square root of t squared, how much is it? Well, that's actually the absolute value of t, which is very unpleasant. We don't like absolute values in our integrals. But we have them because we forgot one important thing. When we do the indirect substitution or the mixed substitution, the functions which we see here must be invertible. And t squared is not an invertible function, unfortunately. So what we need to do, we need to restrict ourselves to a certain integrating range so that t squared becomes a one-to-one function. And we have a choice. We can go for positive numbers, negative numbers, whichever we like better. And when we look ahead a little bit, we will be worrying about square root of t squared. So it makes sense to ask for numbers which are greater than or equal to 0. So this will be the integrating range for our new integral. And now t squared is an invertible function, and the indirect substitution really works. Okay, for non-negative numbers, square root of t squared is just t. So all these square roots are replaced by a t, which is very nice. Then we can also cancel some t's, perhaps. T squared here, t here, t here. This looks very hopeful. So I'm going to write it again. That's an integral. What's on the top? T here, and it cancels. So it's just 2 divided by t plus 1 squared multiplied by arctangent of t dt. Okay, we have a new integral. The substitution worked. That's good. And now we start again. What kind of method should I use? Well, let's see, substitution. Well, what if I call arctangent by some other name? Let's say y. Y is equal to arctan of t. Well, then dy would be dt over t squared plus 1, and I don't see t squared plus 1 anywhere here. So I would have to create it somehow out of this formula. I would have to isolate t from here, obtaining tangent, and putting it... Oh, I don't like it. So this, the way I see it right now, is a blind alley. I don't want to use substitution like that. And is there some other substitution indicated? No, I don't see substitution here. And partial fractions are out as well. So the only thing which is left is integration by parts. That's our last hope. How do we apply it? Well, if I differentiate here, I will have to integrate arctangent, and I don't have it in my dictionary. That would be a tricky proposition. So let's think about it the other way around. If I differentiate arctangent, I get something which actually is different. So this may be a good idea. And then I would have to integrate here, which I'm not really all that happy about, but I can handle it. This is something which can be done. And because it's my last hope, I will go for it. So this will be differentiated, so I will use f in this notation. And if you are used to another notation, you are welcome to use it, no problem here. And for g prime, I'm taking this expression. Now I will be integrating it. And in order to do that, I will write it like that. 2 times t plus 1 to negative 2. That's a nice formula. Okay, let's see. I need to differentiate f. That's easy. And then I have to integrate to obtain g. So I'm integrating and I get 2 t plus 1 to negative 1. I divide by negative 1. It becomes this. Well, it looks quite nice. Here we go. What do I see? F times g. And I'm going to write this one also nicely. So it's minus 2 over t plus 1 times arctangent of t minus integral of product of these two. I see minus here, becomes plus. I see 2 divided by t plus 1 times t squared plus 1 dt. And that's it for integration by parts. Okay, this part is done. I will have to carry it with me. Try not to forget about it. I have a new integral. What can I do about it? Well, actually, this tells me that integration using partial fractions might be the right way to go about it. I definitely don't want to try integration by parts now, although this could be written as a product, but I don't feel like it. How about substitution? I don't really see any room for substitution here. So let's try partial fractions. Okay, I don't want to copy this over and over. So perhaps I will do the partial fractions decomposition somewhere on the side, let's say over here. So what I'm trying to do, I'm trying to take 2 divided by t plus 1, t squared plus 1, and write it as something over t plus 1 plus bt plus c over t squared plus 1. This is an irreducible quadratic term, so I have to put a linear term on the top. Hiding trick, my favorite. T plus 1, the root is negative 1. I hide this, I put negative 1 here, and I get 2 by 2 is 1. That's the one constant which I can get using the hiding trick. Now let's see. I have to go the universal way, so I multiply by this expression. 2 is equal to t squared plus 1 plus bt plus c multiplied by t plus 1. And I need 2 equations. Perhaps I can get 1 out of here. I can try the limit trick. I can get b out of here if I multiply everything by t, and then I send t to infinity. So I put t here, square here, t here, and I send t to infinity, and I get linear divided by cubic polynomial goes to 0, this goes to 1, and this goes to b. So b is negative 1. That's another information which is very useful. And I can also put it here. And now it's time to figure out c, and I will use the plug-in trick. Or perhaps I can try another trick. I didn't talk about it before. I call it the hunting trick. Okay, I'm a hunter and I'm hunting for, well, what am I hunting for? Let's say for t. Let's hunt for t. There is no t on the left. And I'm hunting for t. There is no t over here. I can see minus t, so it's minus 1 times t, and I can see c times t, so it's plus c. So there's that many t's on the right. When I take into account that b is actually negative 1, and I multiply out, I get something like that, and I can see that c is equal to 1. So this completes the partial fraction decomposition, and I can continue. I come back here. It's negative 2 over t plus 1 arctangent t, and then here I have to integrate 1 over t plus 1. I shouldn't forget that there is an extra t now, so perhaps I should remove it again. I don't want to confuse myself. Okay, then there is negative t over t squared plus 1, and there is plus 1 over t squared plus 1 dt. Now we know from the integration using partial fraction chapter that an expression like that, bt plus c over a square expression, should be actually split into parts so that we can integrate it efficiently. Okay, let's make some room. Here we go. Okay, still carry this baggage with me. Minus 2 over t plus 1 arctangent t. And now I will integrate. This is a standard integral. Linear substitution, shift substitution, which yields logarithm t plus 1. Then there is minus, and I'm integrating t over t squared plus 1. And the general advice is to use substitution here. T squared plus 1 can be called, okay, let's say w. We didn't see w yet. Then dw is 2t dt, which almost fits. I can see t dt here. So I divide by 2. It's 1/2 dw is t dt. And this integral becomes integral dw over w and 1/2 in front of it. So it will be 1/2 logarithm of w, logarithm of t squared plus 1. Okay. And this one, it's actually in my dictionary. This is arctangent t. And that's it. I did this part, I did this part, plus c. Okay. And now we should do the back substitution. Can I somehow put it together nicely? There's arctangent here, arctangent. If I put them together, I have to use common denominator. No, it won't be really nicer. So I leave it like that. How about the two logarithms? Can I put them together? Yes, sometimes it's a good idea. Sometimes it's a good idea to put things together. I can factor out 1/2, and then it will be a logarithm, and there will be a fraction. T squared plus 1 drops down, and since I've been factoring 1/2, there will be 2 in front of logarithm, which passes inside as a square. If you don't see it, write it down in detail. Or you can try to take this expression and break it into pieces again, and you will come back here. Okay, so this part is done. This part I like in this compact way. This part is done. Yeah, I guess I'm ready to write the answer. I have to use the back substitution. So t becomes, and here we go, t becomes square root of x. Okay, I'm going to write the answer over here, because I will need room for some other tricks later on. Okay, here we go. I don't like starting expressions with minus sign. I just feel that it doesn't look good. So I'm going to move this arctangent in front, and I will get arctangent of square root of x. That's nice. Then there is minus 2 over square root of x plus 1 multiplied by arctangent square root of x. Then there is plus 1/2 logarithm of t is a square root, so it's a square root of x plus 1, that all squared, divided by t squared, which is just x plus 1. And that's it, plus c. And let's think about it. Okay, how about here? X should be definitely greater than or equal to 0. That's what the square root tells me. And then I look at the fraction and I can see that x should be different from 0. So x is sharply greater than 0. And that's it. That's the answer to our problem. So as you could see, it was quite long, but we could practice all the 3 basic methods in this one example. Yeah, educational. Anyway, let's try a related question. What we have here is an improper integral, which is actually a definite integral with a problem that some of the limits may not be proper. For instance, infinity is definitely not a proper number. And in this example, actually also the second limit, 0, is not proper because we cannot put it into this formula. It's not in the domain. How do we evaluate improper integrals? Well, we start in the usual way. We take some antiderivative, for instance this one, so I'm copying it over here, pasting, and I take it from 0 to infinity. So far so good. Now, we substitute, but now in quotation marks, we sort of substitute improper limit by taking a limit. So we send x to infinity in this formula, which is this formula. Minus limit x going to 0 of this formula. But now we have to be careful. Our function and our integral only exist in the range between 0 and infinity, so we can go to 0 only from the right. And now it's proper. This is how theory handles improper integrals. Okay, let's evaluate. Let's see. The first group. I take x and send it to infinity in this picture. Okay, square root of infinity is infinity. Arctangent at infinity yields pi over 2. So far so good. Minus 2 divided by infinity actually is just 0. Times, and I have to keep going. I cannot just say it's 0, because if we get infinity here, it will be an indeterminate product. So we have to be careful. I put infinity here and I got arctangent of infinity pi over 2. Now I know that this is 0, finally. And we are getting here to this logarithmic part. This is 1/2 logarithm of something. Now what's the something? We are sending x to infinity in this ratio, which we can handle as a separate problem. So if you want, you can write down limit x going to infinity, square root of x plus 1, that all squared, over x plus 1. Now, the type is infinity over infinity, so if you feel like it, you could try to use L'Hopital's rule. Do I feel like it? Not quite. Instead, I will do something else. I'm going to use substitution in a limit. I will take the square root and call it y. Do we have y anywhere here? No. Okay, I can do it. So my new limit has y plus 1 squared on the top, divided by y squared plus 1. And now y goes to, and that's a good question, x goes to infinity. This implies that y also goes to infinity according to this formula. So we have a new limit. And this one is actually nice because it's just a polynomial divided by polynomial. And we know that the outcome at infinity is decided by the leading terms. I can see y squared here, I can see y squared here. This tends to 1. And if you don't trust me, do the L'Hopital's rule here. Okay, that's the first group. That's this limit. Minus, let's open the second group. When x goes to 0 from the right, then the square root yields 0. Arctangent at 0 is just 0. Minus, I put 0 here, 2 over 1, times arctangent at 0 is 0, plus 1/2 logarithm, and I put 0 here, and I get 1. Okay, let's do a little survey. Logarithm of 1 is 0, so this is not here at all. is 0, 0, 0, pi over 2. That's the answer. Here we go. That's our improper integral. No problem. Let's talk about it a little bit more. What if somebody gave me this question right at the start? From 0 to infinity. If you remember, the first trick that we did was substitution. Let's try to apply it here. We will see what happens. Substitution. We use indirect substitution. This may be a good idea. So we take x and replace it with t squared. dx is 2t dt. And we restricted ourselves to t greater than or equal to 0. That was the setup. And after we did it, do I still remember it? There was arctangent of t, definitely. And there was t plus 1 square, I remember. And then this power and these powers, they disappear, they cancel, there was 2 on the top. Does it look familiar? dt, important. Okay, I think that's it. But now, this integral was definite, and therefore we have to also change the limits. X is equal to from 0 to infinity. And now let's talk. Okay, t is a square root of x because t is non-negative. So square root of infinity is infinity, and square root of 0 is 0. Zero. These are the new limits. So we have a new improper integral, and we could evaluate it in this way, do the calculations and so on. Now what is the advantage? Well, we would have to go back to the language of x. So our solution could have stopped one line earlier, which could save us some work, especially if the solution is very long. So this is a really good idea. By the way, here is another benefit, but this is not guaranteed, but sometimes you get lucky. When you look at this new integral, you can see that infinity is still an improper number, so this is an improper integral. But 0 now doesn't cause any trouble. Here, 0 did cause trouble. This is nice. That's a bonus. As I said, sometimes it happens. So it means that after we calculate the outcome, and we are at this stage, we have to substitute infinity using limit, formally, but 0 can be substituted directly. We don't have to play with the limit. We simply put it there, which is actually how we evaluate limits. We put it there, but there is a difference from theoretical point of view. And that's it. I don't think I can milk this example for anything more. So this concludes our story about integration. It's done.